Stars, such as our Sun, exhibit a vast array of shapes, sizes, colors, and phases throughout the cosmos. Within the Milky Way galaxy alone, estimates suggest a staggering 100 to 400 billion stars inhabit our singular medium-sized galaxy. Astronomers extrapolate from images captured by Hubble's ultra-deep field that the observable universe hosts upwards of 200 billion galaxies. As one contemplates these figures, the enormity becomes daunting. Consider this: the estimated total number of stars in the universe reaches a mind-boggling 1 septillion, depicted as 1 followed by 24 zeros. That makes my brain hurt. Every star begins as a stellar nebula. These nebulae are vast clouds of gas and dust floating in space. They are the birthplaces of stars. Within these clouds, gravity pulls gas and dust together into clumps. As these clumps grow denser, they heat up and eventually form into protostars. The remaining gas and dust surrounding the newborn stars is the matter that can form into planets, moons, and other celestial objects. Stellar nebulae often exhibit beautiful colors when viewed through telescopes due to the way different types of gas and matter emit light at different wavelengths. Similar to how a raindrop forms from a cloud, a protostar forms as gravity pulls cosmic matter together in a stellar nebula, and it begins to heat up and spin faster. This spinning motion flattens the cloud into a disk shape, also referred to as a T-Tauri star, with the center becoming hotter and denser. The protostar continues to grow as it accumulates more material from its surroundings. Eventually, when it gathers enough mass and pressure at its core, temperatures rise to millions of degrees Celsius and nuclear fusion ignites, and the protostar officially becomes a main sequence star, shining brightly in the sky. A main sequence star is like the dependable middle-aged adult of the stellar world. It's a stable, long-lasting star that's actively fusing hydrogen into helium at its core. This fusion process creates a delicate balance. The outward pressure from the fusion reactions counteracts the inward pull of gravity, keeping the star stable and preventing it from collapsing. Main sequence stars, like our Sun, spend most of their lives in this phase, providing the steady light and warmth necessary for life to thrive on orbiting planets. Low and medium mass main sequence stars, like the Sun, typically have two outcomes, eventually becoming a red giant or a brown dwarf. Brown dwarfs are indeed an important class of objects in astronomy, often described as failed stars or substellar objects. They're not massive enough to sustain hydrogen fusion in their cores like main sequence stars, but they're more massive than gas giants like Jupiter. As a main sequence star like our Sun ages and consumes its hydrogen fuel in the core, the balance between gravity pulling inward and nuclear fusion pushing outward begins to shift. With less energy being generated from fusion, gravity starts to compress the core, raising its temperature. Meanwhile, the outer layers expand and cool, causing the star to swell up, becoming a red giant. This expansion happens because the outer layers are pushed outward by the increased pressure in the core. Red giants are much larger and cooler than main sequence stars, with their outer atmospheres expanding outward into space. As a red giant sheds its outer layers, it forms a colorful cloud of gas and dust, known as a planetary nebula, which eventually begins the process of star formation all over again. The core left behind condenses to become a white dwarf, a dense Earth-sized remnant composed mainly of carbon and oxygen. This is the final fate of most stars like our Sun. White dwarfs slowly cool over billions of years, fading into obscurity as a cold black dwarf, no longer emitting significant light or energy. It's important to note that black dwarfs are primarily theoretical objects, since the universe may not even be old enough to have even witnessed such a long process. Supergiants are even larger and more massive than red giants, often hundreds of times more massive than the Sun. These massive stars evolve from main sequence stars with much higher initial masses than our Sun. As they age and exhaust their nuclear fuel, they undergo similar processes to red giants, but on a much grander scale. The core condenses and heats up, while the outer layers expand even further, sometimes reaching hundreds of times the size of the Sun. For supergiants, the end phases of their life cycle are quite different. No fizzling out and drifting off into obscurity. For supergiants, their lives end in much more epic proportions as a supernova, a neutron star, or a black hole. When a supermassive star reaches the end of its life, its core collapses under gravity's immense pressure. This happens in a fraction of a second, causing the core to rebound, sending out a shock wave that blasts the star's outer layers into space. These heavy metals and elements expelled by the supernovae are crucial for the synthesis of forming planets and life. This explosion releases enough energy to outshine entire galaxies for weeks. The remnants of the supernova can either form a neutron star, or if the core is extremely massive, it collapses further into a black hole. A neutron star is like a city-sized cosmic powerhouse. It forms when a massive star undergoes a supernova explosion, leaving behind a dense core composed mostly of tightly packed neutrons. These stars are incredibly dense. Just a teaspoon of neutron star material would weigh as much as a mountain on Earth. Their gravity is so strong that even light can't escape, making them invisible to the naked eye. Neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses, which are called pulsars. Not all, but most neutron stars are pulsars. Their intense magnetic fields can wreak havoc on nearby space, creating some of the most extreme environments in the universe. If the density of this neutron star surpasses a certain limit, its core can continue to collapse in on itself, packing an immense amount of mass into a tiny space. Such tremendous pressure can birth a black hole. The gravity at its center becomes infinitely strong, creating a region called a singularity, where space and time seem to vanish. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Black holes gobble up anything that strays too close, distorting space and time around them, and leaving behind a mysterious shroud of darkness in the universe. There's so much more to explore in the life cycle of a stellar body that we've only just begun to scratch the surface here. Keep searching, friends. I hope you enjoyed the video. Please like and subscribe to support the channel so we can continue to make content like this. Thanks for watching.